My name is Emma Warren, and today I will be presenting my lab on the macroscopic view of DC and RC circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel form, then compare those values to the actual values calculated using an online circuit construction kit. My predicted values were 0.02 amps, and my findings through the simulation were also 0.02 amps. It is apparent that these numbers are exactly the same. The first important concept is Kirchhoff's voltage law, also known as the loop rule. This rule states that the total voltage around a closed loop is 0 volts. This is due to path dependence, which can be seen here as the loop begins and ends in the same place. A second concept that is important to this lab is Kirchhoff's current law, also known as the node rule. This states that the current flowing into a cluster must equal the current amount that is exiting that cluster. Finally, Ohm's law, which is voltage equals the current times the resistance supplied by the conductor, is important to this lab to calculate changing current. Now let's discuss the experiment. My system was a circuit and the surroundings were everything around it. My assumptions included that there was no resistance from the wires, batteries, or from meters. For my procedure, I created the circuit as instructed with two 1.5 volt batteries, two ammeters, and the two resistors with 47 and 100 ohms respectively. I found that my predictions were correct with the ammeters reading 0.02 amps. I also found that if you switch directions of the ammeter, it will read the same value, only negative. Then I replaced an ammeter with a voltmeter creating an open circuit. This leads to the ammeter reading 0 amps because there's no current flowing through the circuit, as that is the nature of open circuits. The voltmeter recorded 3 volts due to the sum of the volts provided by the batteries. Next, I used the voltmeter to measure the potential difference between each point around the circuit. I found the values listed and their sum totals to 0 volts. This makes sense due to the loop rule, where path independence declares no change if you begin and end in the same position. When replacing the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current of the ammeter increases to 0.06 amps. This is because the ammeter has less resistance than the resistor, which increases the current that goes to the ammeter. Finally, I calculated the resistance of each element based on experimental values and the use of Ohm's law and found the following. For 47, I found 48 ohms. 100, I found 102 ohms. For the ammeter, I found 0 ohms. And for the wire, I found 0 ohms. Moving on to RC circuits, to test them I used two different bulbs and watched their behavior as capacitors charged and discharged. When a battery is connected, light is emitted but slowly diminishes until current ceases completely. When the battery is disconnected, the capacitor is able to discharge, changing the direction of current and briefly lighting the bulb. When I tested on a 10 ohm bulb, I found that it took 11.7 seconds to charge and 12.5 seconds to charge. And when I tested this on a 20 ohm bulb, I found that it took 22.5 seconds to charge and 24.2 seconds to discharge. Next, to determine the value of RC, I plotted the change in potential at different times, used the given equation, and linearized it to create my graph. I then found the slope and used the equation slope equals -1 over RC to determine RC. I found that the experimental RC was 5.988 seconds, and the expected, using the equation of ohms times the capacitor value, equals 6 seconds. Finally, let's answer some discussion questions. What if you were doing this experiment in real life and used an actual ammeter instead of the ideal simulated ammeter? What difference about real ammeter and how would it have affected the circuits you hooked up to it? While the simulated ammeter has no resistance, a real ammeter would provide resistance. This would result in a decrease in current flowing through the circuit. Next, what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? A real battery in an ideal simulation would result in instant charge of the capacitor. However, this is not the case in real life. In real life, this would not happen as you must take into account the resistance of the wires, meters, and other tools involved in the experiment. In conclusion, in this lab we discussed Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, the difference between parallel and series circuits, and the behavior of ohmic resistors and capacitors. I hope you were able to learn something along the way. Thank you for listening.